Welcome to Chapter 15. We are going to be discussing nuclear magnetic resonance spectroscopy, also known as NMR. We're going to be looking at the hydrogen nucleus and the carbon nucleus. But in this first video, we're going to talk a little bit about the background and the experiment itself. All right, so when we looked in the last chapter at IR, we looked at how infrared, let's switch to a pen. We looked at infrared spectroscopy and how IR radiation affects bonds, right? Causes stretching and vibrating, which can be characteristic to specific bonds. With NMR, we are using radio frequencies to assess the nucleus of certain atoms' environment. Now, that may sound like I'm just saying words at you right now, but it'll make sense as we go through this experiment. Being able to identify the environment of different nuclei, whether it's hydrogen or carbon, gives you information about how an alkane, alkyne, how an organic molecule is put together, right? Knowing that there is a functional group is great, but how many methyl, ethyl, isopropyl groups are there, and where are they in relationship to other functional groups? This is where NMR can be really helpful. It's a very robust technique, so it's a little bit more complicated to learn. So we're going to take it a step at a time. You can focus on many different nuclei. We're going to focus on carbon and hydrogen because we're organic chemists, and that's going to be the most helpful. But you can definitely study other nuclei as well. What you need, what is necessary for NMR to be possible, is to have a nucleus with an odd mass number. Now, I struggle with my Gen Chem students to remember what mass number is, but it's just the sum of the protons and the neutrons. So not all isotopes can be studied this way. Only isotopes that have a nucleus with an odd mass number. So proton NMR is great. Hydrogen has one proton, no neutrons, and therefore it works great. Carbon is a little bit trickier because carbon-12 cannot be studied by NMR, but carbon-13 can be. And since carbon-13 is naturally occurring, though granted and it's much less abundant, it can be studied with NMR. You also have some other common nuclei that are studied by NMR. Now, the reason that it has to be odd is because when you spin this odd nucleus, it creates a magnetic moment, and this magnetic moment is critical for the experiment to work. So, right, a magnetic moment also just really means a magnetic field. We are going to manipulate or exploit that magnetic field in this experiment. What you need to take away from this right now is that these are the two nuclei that we're going to study, and only nuclei with an odd mass number can be studied in this way. Now, as we talk about a magnetic moment, let's look at this image here on slide 4. When you spin a charged particle, it is going to create this magnetic field when you have a nucleus that has a magnetic moment, and that magnetic field's very similar to what you see here with just your standard bar magnet. There's a north end and a south end, and that's going to be important as we look at the experimental design. So when we think about the NMR, right, there's layers to this setup. So when we look at this box right here, what we're saying here is that we have a sample and it is spinning, right? It's in the NMR instrument and it's spinning. And every nucleus that has a magnetic moment is creating its own little magnetic field. And as it's spinning, it's like a bag of bar magnets. All of these magnets are they've got a magnetic field, but they're tossing and turning and they're in different directions. In the blue box, what you're seeing is it's spinning, plus you have an external magnet, right? That external magnetic field is going to cause all of your little bar magnets to line up. Now, some align with the field and some align against, but it's no longer this sort of chaotic, random bag of magnets, right? There's more order here. Now, let's talk about these little indicators. So first we have our sample. We are setting it to spin. We are turning on the external magnetic field, right? Now, once we've turned on that magnetic field, your nuclei are going to be in one of two categories, the alpha spin state or the beta spin state. All right, so they are going to line up, but they don't all align the same. The alpha spin state is with the field. All right, so you notice the applied magnetic field is an up arrow. All of your alpha spin states are up arrows. Beta spin state is against the field. More of your nuclei will align with the field than against, but the fact that some higher energy nuclei will go against it just happens. It is possible. And again, something that's just part of this experiment. All right, so the experiment's not over. This is just the setup, right? So you prepare a sample, the instrumentation causes it to spin, you apply a magnetic field, you have all of these little magnets that are lined up with and against the field. What's next? So from there, we are going to apply radio frequencies, right? Radio waves. We're looking at the radio portion of the electromagnetic spectrum. Now, there is a characteristic energy difference for nuclei in certain environments between their alpha and their beta spin states. So this ought to start looking a bit familiar after talking about IR and talking about spectroscopy. There is going to be a photon of radiation that will allow the alpha spin state to flip to the beta spin state, right? So the radio frequencies, I'm going to put, let's see, we'll just say radio waves, absorbed by any of your alpha spin state nuclei will flip to the beta spin state, right? But only if they get a photon that matches this energy gap, right? So any nucleus that is in this same spin state here will absorb a certain radio wave and flip over to the beta spin state. That's how we're going to be able to analyze the different nuclei. When an atom, okay, so this slide is just explaining what I just said, right? Those radio waves with just the right energy will flip alpha to beta. Now, okay, so you might be thinking, well, how does this help us? Wouldn't all hydrogen nuclei be the same and would flip from alpha to beta? And luckily for us, that's not the case. So let's take a really simple molecule here and let's look at bromoethane. There are two different kinds of hydrogen in this molecule because as that little nuclei is spinning and creating its own magnetic field, there are electrons around that nucleus that are also charged, also spinning, also creating their own magnetic field. What that does is that creates a barrier to this external field here. So you're going to hear the word shielding and deshielding, shielded and deshielded a lot in this discussion. Those little electrons around the nucleus create their own little magnetic fields that shield the nucleus from feeling that external magnet to some extent. The more electron density you have around a nucleus, the more shielded it is. And it will require less energy to spin flip. All right. Nuclei that have less electron density are deshielded. They feel this magnet more strongly and they require a different energy. So even though all of these hydrogens in this example are hydrogen, they are not in the same electronic environment, right? This bromine is going to be pulling electron density away, and these hydrogens here, we'll label them A, will be more deshielded because they're close to bromine. Whereas your little HB protons down here, right, on your CH3 group, are going to be more shielded. More electron density will be around them because they're not as close to the bromine. So the energy gap, how much energy it takes to flip the A hydrogen versus the B hydrogen, is going to be different. And so we can start to tell about the structure of an organic molecule this way. Now, I want to talk about the R in NMR for just a moment. Nuclear magnetic resonance. This is the only time resonance is used in organic, and it means something different. We are not talking about resonance structures. We are not talking about Lewis structures. The resonance in NMR is referring to that flip from alpha to beta. When you are flipped into the beta spin state, it is said to be in resonance. It has nothing to do with the definition of resonance as you know it from Organic 1. For the most part, I'm just going to say NMR, so nothing to stress out about. Now, acquiring this NMR spectrum requires a pretty strong magnet, but there's a lot of variety in NMR instrumentation. We can go from the 60 megahertz magnet that we have at Blinn to 500, 600, and beyond megahertz magnets. This, of course, makes instrumentation much more expensive. It also makes it higher resolution. Now, when you change the magnet, these gaps change. But lucky for us, we live in a time where the computer is going to handle this. So whether an NMR was run on a small magnet or a large magnet NMR, you're going to read the spectrum the same. So we're not going to have to worry about that. The information that is collected from the instrument is, what's the word I'm looking for here? I'm sorry. It is analyzed, or it is dealt with by the computer, and you use something called Fourier transform. You might see that also when you talk about IR. It is a way to take scans from the NMR and handle them and do some fun math and give us something that we can read. So the emitted energy as the beta spin state nuclei relax, they give off, right, that radio wave, that photon, that is that amount of energy that you expect to bridge the gap. and it's collected and it's recorded as something called an FID. Now, you might never have to deal with an FID. FIDs look something like this. I think there's a picture on, nope, there is not a picture. Okay, FIDs I couldn't teach you how to read, but FIDs are then treated, through the computer programming into an NMR spectrum, and that's what I'll teach you how to read. Let's see. Okay, now a lot of that goes on in the computer, it's important. We often have to take multiple scans and then have them averaged together to get signals to come above the noise. Now with proton NMR, you may not need very many scans. Something like carbon NMR, where you're having to focus on carbon-13, which is only 1% abundant, you may have to take many scans. So an anecdote I usually drop in here when I'm face-to-face is I used to run NMR all the time in graduate school, and a proton NMR on a 500 megahertz instrument took maybe 10 minutes, whereas a carbon NMR could take 12 hours. You just have to take a lot more scans when you don't have as much of the nuclei to study. So the actual experiment itself has a lot of variables to set up. Now, I do want to stop here and show you this. This is a picture of a standard NMR. Now, the size of this really varies depending on the magnet. I've worked with a 360 megahertz magnet, and it came up, to about my shoulder, and I'm 5'6". That gives you some perspective. I also worked on a 500 megahertz NMR, and I had to use a step ladder to get up to this top portion. This right here is where the sample goes in. And then it will spin inside, and then you've got a magnetic field in here, and there's layers of nitrogen and helium. It's very exciting. All hooked up to a computer. Oh gosh, that's what I was talking about. That's an FID. Not very easy to read anything from that. We'll let the computer do that. All right, now, why are they showing me this little compound right here? If you have a compound that you're studying and it's a liquid, then you're great. But a lot of times we're trying to study solids, or we don't have enough liquid to fill up an NMR sample tube. So we may have to dissolve in a solvent. If you're trying to study hydrogen and your solvent has hydrogen in it, all you're going to see is solvent. So you have to pick, appropriate NMR solvents. Cannot have a large a nucleus that's going to show up in great abundance. Now, the carbon isn't a huge problem because, again, 1% C13. Chlorine is not going to be studied here, but deuterium is going to be needed to replace hydrogen, right? Deuterium is hydrogen, but with a neutron, right? So it has a mass number of 2, no magnetic moment, and so it's not going to show up on the NMR. So an appropriate NMR solvent should have no hydrogen. And so a good NMR solvent, oftentimes you need hydrogen for just solubility issues. And so deuterated solvents are really useful. So you might see something like deuterated chloroform, or CdCl3. You might see heavy water, D2O, right, etc. You just don't want something with hydrogen. So anything with hydrogen needs to have deuterium replaced. In the next video, we will get into characteristics of the actual NMR spectra, and we will talk about the number of signals, signal location, and intensity. And then in video 3, we will get into that signal shape.